This is Lesson 11 in our Calculus 2 series, Trigonometric Integrals. In this lesson, we're going to be solving integrals that are products of powers of trig functions. And the key here is to use trig identities to transform the integrals into basic integrals or easy U substitution integrals. So for example, these are the types of integrals that we're going to be looking at in this lesson. And the identities that we need are here. Sine square x plus cosine square x is equal to 1. Now, if we divide this entire equation by cosine squared x, we get tan squared x plus 1 equals secant squared x, and that's another important identity for us. We have sine squared x is equal to 1/2 of 1 minus cosine 2x. Cosine squared x is equal to 1/2 of 1 plus cosine 2x. And the way that I remember the difference between these two formulas is this I in sine, I think about the minus sign here. And sine 2x is equal to 2 sine x cosine x. So these are typically the identities that you're going to see that come up in these types of integrals. And we're also going to need a couple of other integrals to help us complete these solutions. And this is one of them. The integral of secant x is ln of absolute secant x plus tan x plus a constant. And we can see this by taking the derivative of ln absolute secant x plus tan x plus c. The derivative of ln of a function is 1 over that function multiplied by the derivative of that inside function. So the derivative of secant x is secant x tan x, and the derivative of tan x is secant squared x, so we're here. And then we can factor out a secant x in the numerator, and that gives us secant x times tan x plus secant x, and then these will cancel, and we get secant x. We'll also need the secant reduction formula, which allows us to reduce the power of the secant x that we're trying to integrate. So if we had a secant x to the third power here, we could use this formula, and then we have to take the integral of secant x to the first power. If we start with n equals 3, then here we're going to have secant x to the first, and that we know how to integrate. It also applies to n greater than 3, and we can start with, for example, secant to the 7th power here, and then end up having to integrate secant to the 5th, which we could reduce again to secant to the 3rd, and then reduce again to secant x. And this formula comes from integration by parts. It's actually a circular by parts problem. So let's take a quick look at that. We're going to consider this secant to the nth power as secant to the n minus 2x multiplied by secant squared x dx. So that u is equal to secant to the n minus 2x and dv is equal to secant squared x dx. And computing du, the n minus 2 comes down. We're using the chain rule. This is n minus 2 secant x to the n minus 3 power multiplied by the derivative of secant x, and that's secant x tan x. And then we have our dx. And simplifying, we get n minus 2 secant to the n minus 2x tan x dx, and that's our du. And then from dv, we compute v to be tan x. So then using the integration by parts formula, we're here. But the integral that we're left with doesn't seem any simpler. When we use a trig identity, though, with tan square x equaling secant square x minus 1, it does simplify and reduce to integrals only in powers of secant x. So then notice when we have secant to the n minus 2x and secant squared x, when we multiply this through, we're getting n minus 2 secant to the n x. So I'm separating this into two integrals when we distribute here. And then multiplying through by the 1, we're here. And so now we're looking at our original integral, calling that I, and then we have here n minus 2 times I. And I'm not going to worry about the constant that these may differ by, because we still have this integral, which is going to give us a constant of integration. So we don't need to put in an extra constant here. So then bringing this to the other side, we've got I plus n minus 2i is equal to these remaining terms. And so combining here, this is n minus 2 plus a 1, and so that's n minus 1i is equal to this. And then dividing by n minus 1, we have our secant reduction formula. And we'll see an example of how this is used later on in the lesson. And also, just for completion, I want to remind you that the integral of tan x is negative ln of absolute cosine x plus a constant, or this can be written as ln of absolute secant x plus c. And remember that that's found by using u substitution. We have tan x is equal to sine x over cosine x, and we let u be cosine x. And so we get negative ln of absolute u plus a constant, which is negative ln absolute cosine x plus a constant. And remember that this negative 1 can be brought up as an exponent of the cosine x, and so this can be written as ln of absolute secant x plus c. And note here that this negative 1, I'm talking about an exponent, I'm not talking about an inverse function. And it's actually because of this confusion that I typically don't use sine inverse of x or cosine inverse of x notation. I use exclusively the arc sine x notation and arc cosine x notation. But anyway, so here we have our integral of tan x. And so all the stuff that's been highlighted, that's all the tools we need to solve these trig integrals. And so let's take a look at some. Here we have integral of sine to the 6th x cosine to the 3rd x. And so my advice with integration has always been, if it's not a basic integral, look for a composition of functions to use u substitution. And so what compositions do we see here? We see sine x taken to the 6th power. We also see cosine x taken to the 3rd power. So at first, it might look like we have two options. Let's explore them. If we let u be equal to sine x, then du would have to be cosine x dx. And so let's see if that could work here. If we let u be sine x, then we're going to have u to the 6th here. And then one factor of cosine x is going to be used with dx for du. And we're going to have an extra cosine squared here. But that's okay, because we can make a replacement. Cosine squared x is equal to 1 minus sine squared x. And this is 1 minus u squared. So our original integral, we're going to break up the factors of cosine here so that we can break off our cosine x dx that we need for du. So I'm going to write this cosine to the 3rd x as cosine squared x, cosine x. And so here we're going to have u to the 6th. Here we're going to have du, and this we need to use the trig identity. So here again we have u to the 6th. And this becomes 1 minus u squared, and then du. And now this is just polynomial. We can just multiply through the u to the 6th, and it's a basic integral. And so we integrate, and we write it back in terms of x, and that's our solution. So we started this by identifying a composition, and we let u be sine x. Now, you might be wondering, well, what if we let u equal cosine x? Will that work? Let's take a look. If we had u equal to cosine x, then du would be negative sine x dx. But then look what would happen. We'd have to break off a sine x to go with dx for du, and then we're left with sine to the 5th x. But we can't replace sine to the 5th x with anything about cosine x. We can only do that for even powers. We know that for every sine square x, we can make a replacement 1 minus cosine square x. But we have sine to the 5th, and that's an odd power, so that's not going to work for this integral. Since this power is odd, we can't replace it with cosines. So in this integral, it's not going to work. However, if we had sine to the 5th x, cosine to the 3rd x, then we could do it either way. So let's take a look at this one. If we have u equals sine x, as we did in the last problem, we'll get u to the 5th times 1 minus u squared du. And so we integrate just like we did in the last problem, except here we have sine to the 6x over 6 minus sine to the 8x over 8 plus a constant. Or, in this case, we could use u equal cosine x, and then du is negative sine x dx. And so we want to break off a factor of sine x to use with dx for du. We also want to multiply by a negative on the inside and on the outside so that we can make our du. So here I have a negative on the outside, sine to the fourth x. I broke off the other sine factor, put that here with the other negative sign. And we have cosine to the third x. And so sine to the fourth x we can recognize as sine squared x quantity squared. And sine squared x is 1 minus cosine squared x. So now we broke off the one factor of sine x that we needed for du, and everything else we're trying to get in terms of cosine, because if we can get it in terms of cosine x, then everything can be written in terms of u. So we replaced this sine square x with a 1 minus cosine square x, and now we can change it into u's. So we have 1 minus u square, quantity squared, u to the third, du. And we still have our negative sign on the outside. Now, in order to integrate here, we just need to multiply it through. So we need to square this out and then distribute the u to the third. And so we're here. And that's a basic integral. And so we're here. Replacing back into x gives us this. Now, it looks like a different solution than if we would have had u equals sine x. With u equals sine x, we would have gotten sine to the 6x over 6 minus sine to the 8x over 8 plus a constant. And here we're getting a bunch of cosine terms. Notice I used a different constant because I want to make it clear that these two functions probably differ by a constant. And actually, instead of going through the trig identities to try to prove that they're equal, I would encourage you to graph both of these using a graphing utility, and you can see that these two functions differ by a constant. So it does make sense that these are both solutions for the same integral, of course, with different constants. Now let's take a look at another example. Here we have integral sine to the fifth of 2x over radical cosine 2x. Now the first thing I notice here is that we have a 2x inside our trig functions. But both trig functions have the same argument. They're both of 2x. So we don't need to make any adjustments. We're just going to deal with the 2x there. If one of them was a 2x and the other was an x, then we would have to worry about using a double angle formula to get them both in terms of x, or both in terms of 2x. We would have to make some kind of trig identity there. But because these are both 2x's, we're good. And so let's write this as a product of powers of trig functions. So we have sine of 2x to the fifth multiplied by cosine of 2x to the negative 1/2 power. And we look at this and we see two compositions here. We see sine of 2x taken to the fifth power and cosine 2x taken to the negative 1/2 power. Now, if we were to let sine 2x be equal to u, we would need a cosine 2x as part of our du, right? We would need 2 cosine 2x dx. But we only have cosine 2x to the negative 1/2 power. We don't have it to the first power here. So that's not going to work. Our only choice would be to let u equal cosine 2x and then work with the remaining powers we have here of sine 2x. So we let u equal cosine 2x, and so du is going to be negative 2 sine 2x dx. And so we want to break off a factor of sine 2x to keep it with dx. We also want to multiply in a negative 2, and so a negative 1/2 on the outside. So from here, we take off a sine 2x power, and so this is now to the fourth power, and we bring that over here to write it next to dx. We also put in a negative 2, and on the outside, a negative 1/2. So now we're here. And now, how are we going to get this sine 2x to the fourth power in terms of cosines? We need to be able to write all of this in terms of u. Here we have u to the negative 1/2. This is du. How are we going to get this in terms of u? We need to use a trig identity here to get this in terms of cosine 2x. So we recognize that sine 2x to the fourth power is sine squared of 2x quantity squared, and that sine squared 2x can be written as 1 minus cosine squared 2x. And so we've got this squared. And now it can all be written in terms of u. So we have negative 1/2 integral of 1 minus u squared, quantity squared, times u to the negative 1/2 du. And so we need to square out here and then distribute our u to the negative 1/2. And then it becomes a basic integral. So now we're here, simplifying and writing it back in terms of x, we're here, and this is our solution. Let's take a look at another example. We have sine square x. So we see a composition and we think about letting u equal sine x, but then du would be cosine x dx, and we don't have that. And we can't replace sine squared x by 1 minus cosine squared x, because then we'd be stuck with 2 copies of cosine x, and that's not going to work either. So we need to have a different solution here. So this is where this identity comes into play. Sine square x is equal to 1/2 of 1 minus cosine 2x. Notice that here we have a sine square x, and we can't integrate that on its own. But then we're going to replace it by a cosine 2x, and that we can integrate. It's only cosine to the first power. That becomes a basic integral. So the sine squared x gets replaced by 1/2 of 1 minus cosine 2x, and integrating, the 1 becomes an x. Here we have a 1/2 sine 2x, and plus a constant. Distributing the 1/2 on the outside, we're here. And of course it gets a little bit harder than this. Suppose we have integral sine to the 4th x dx. Again, if we let u equal sine x, we're not going to be able to have our du, our cosine x dx. So we recognize the sine to the 4th x as sine squared x squared. And so we replace the sine square x by 1/2 1 minus cosine 2x. Now we have to be careful here. We need to square this out properly. This 1/2 also gets squared, and so we have a 1/4. And then squaring this out gives us 1 minus 2 cosine 2x plus cosine square of 2x. So notice that we've got 2 terms here that we can integrate, but we're still stuck now because we have a cosine squared 2x. And we don't have a sine x to go with it to make a du. So we need to use the corresponding formula for cosine square x. So our formula says cosine square x is equal to 1/2 of 1 plus cosine 2x. But notice that our angle here is 2x, and so we've got cosine square of 2x. That means we need to replace it with 1/2 of 1 plus cosine 4x. So that goes in here. We can distribute our 1/2, combine the 1 plus the 1/2, we get 3/2, move this 1/4 to the outside, and so we're here. And now we have basic integrals. And so this becomes 3/2 x. This is 2 times 1/2 sine of 2x, and this 1/2 stays, and we have 1/4 sine of 4x. And so we simplify, and then plug in our bounds, and we get 3 pi over 16. Let's take a look at another. Integral from 0 to pi over 4 of radical 1 plus cosine 4x. Now we see a composition, so we might think about letting u equal 1 plus 4x, but then with that we would have du to be negative 4 sine 4x dx, and we don't have a sine 4x here with dx. So that's not going to work. So we have to think about 1 plus cosine 4x as being 2 cosine squared of 2x. Remember, the formula we just looked at was cosine square x is equal to 1/2 of 1 plus cosine 2x. So if we have 1 plus cosine 4x instead, 1 plus cosine 4x, that means this angle is then a 2x. And so multiplying both sides by 2 here, we can replace the 1 plus cosine 4x by a 2 cosine square 2x. So we're here. So this becomes radical 2 times radical cosine 2x quantity squared. Now when could we cancel this radical and square? Remember, we can cancel that when cosine of 2x is positive. And in fact it is here because we're on the interval from 0 to pi over 4. And on that interval we're talking about cosine of 0 to cosine of 2 times pi over 4, so that's cosine of pi over 2. So we're talking about cosine values here, and we can see that they are greater than or equal to 0. So we can simplify that to cosine 2x, then integrate and plug in our bounds. And so we get radical 2 over 2. Now let's take a look at some combinations of secant x and tan x. Here we have tan to the third x secant x dx, and we see a composition here, so we might think, let's try u equals tan x, the inside function. In that case, du would be secant squared x dx. But we don't have a secant squared x, and we wouldn't be able to get one either, even if we recognize this as tan x times tan squared. The tan squared will get replaced by a secant squared x, but then we have another factor and we have secant to the third. So we're still going to be stuck. That's not going to work. So let's try it the other way. Let's try letting u equal secant x and seeing if we can work with that. If u is equal to secant x, then du is going to be secant x tan x dx. So we have a secant x already. Let's pull off one of these tan x factors and write it this way. So we have tan square x secant x tan x dx. So now here we have a du. But what do we have here? We have a tan square x. We need this to be written in terms of secants. Well, we know that tan square x is secant square x minus 1. And so we have a u square minus 1 multiplied by du. And so now we can integrate. That's a basic integral. And we're here. Let's take a look at another. Here we have tan square x secant to the fourth x dx. Again, we see two different compositions. We see tan x to the second power, and we see secant x to the fourth power. So let's consider the options. If we let u be tan x, then du would be secant square x dx. So if u is equal to tan x, then du would be secant square x dx, and we would have an extra secant squared x, and that's okay because it would get replaced by a tan square x plus 1. So this would be a u square plus 1, and that should work. Let's take a look at the other option. If we let u equal secant x, then du would be secant x tan x dx. And so we would have to pull off one of these factors of tan x, but then we'd be stuck with an extra tan x. We can only make a replacement for tan squared x in terms of secants, or for even powers of tangent x. We can't make a replacement for just tan x, so that's not going to work. So this side's not going to work, and we're going to stick with this. So let's let u equal tan x, du is secant square x dx, and so we want to break off a secant squared here to keep it with dx, and that's going to be a du. And this is going to be a u squared, and this we need to use a trig identity on. So we write that secant square x as a tan square x plus 1, and now we have u squared times u squared plus 1 du. And so we multiply through, integrate, and write it back in terms of x. Let's take a look at another one. Tan square x secant to the third x. If we let u be tan x here, then du would be secant squared x dx. And then we would have an extra copy of secant x, so that won't work. If we let u be secant x, then du is secant x tan x, and then we're going to have an extra copy of tan x, so that's not going to work either. So this is the kind of problem in which we're going to use the secant reduction formula. We're going to get this only in terms of secant x, and with that we'll be able to use the reduction formula to whittle it down to integrals that are solvable. So let's write this tan square x as a secant square x minus 1 and multiply that through, and so we're here. And now let's separate these two integrals. For the secant to the fifth x, we're going to use the secant reduction formula, and we get 1/4 secant to the third x tan x plus 3/4 secant to the third x dx. And that's again by secant reduction formula. And notice we didn't touch this yet. This is just the integral of secant to the third x. So we can combine these two. We have positive 3/4 minus 1. That's going to give us a negative 1/4 of that integral. And so now we're here. But how do we solve this integral, secant to the third x? We use the reduction formula again. So now this is getting replaced by this, by the secant reduction formula. And now we're left with integrating secant x, which we showed above is ln absolute secant x plus tan x. And so now we've completed our integral. So again, all of these trig integrals are going to be solved by using trig identities to get these integrals either into basic integrals or easy use substitutions. And it takes a bit of practice to get good at these, so I encourage you to do lots and lots of exercises. And this concludes our lesson on trigonometric integrals.